Hello, this is the final update for the project about the finite element analysis for a truck's chassis. And for modern days, since transportation safety is a huge concern, we need to analyze the structural rigidity of the chassis. And it was ruled by NHTSA. And for simulation reasons, we need to make assumptions, and we can process the structure analysis with the CAD modeling. The objective is to construct a basis infrastructure to present a crash analysis on the chassis of the truck. And with modular input and repeatable solution strategy, the model can be modified and adapt to any situations as a universal tool. And the way we do the analysis is by using finite element analysis. And since from the first result, the plasticity is not shown on the result, we need to put an arbitrarily large impact to show the validity of the process. And for the geometry, we downloaded from the open source modeling site for academic fair use, and with all the mesh and seeding done in Abacus AE. And for the material properties, since Abacus is pretty picky on what is going to be good for the analysis, so I fetched the physical property from a tutorial for Abacus. And the first line need to be modified since Abacus do a syntax check, and then this is as close as I can get to the physical property. And for the governing equation, I did a hand scratch calculation for the pure impact for the truck, because the force is only facing the chassis without any other direction like vertically and horizontally. So it's basically a compressed beam problem with all the governing equations as follows. And for analytical solution, I have time to do it, and then it proves the concept of how valid the assumptions and the model is. And based on that, since the stress is about 3.2 gigapascal, the value should be valuable for the analysis. So for finite element, I dig a little bit deeper into it and then know a lot of fundamental principles from it. So these are what I was using for the analysis. And then since we're using the weak form, the formulas can be derived as follows. And for the boundary condition, it's relative to the real life situation, since the crush is gonna be on the front of the vehicle, and the front wheel seems to be the first constraint of the model. And since that, I fixed the vertical displacement, and then for the completeness of the model, I'm gonna fix the tail of the chassis to no degree of freedom, so pinned, for the analysis to run. And for the loading scenario, in the appendix, I did an analytical solution, and we can see from above, so it's 604 kilonewtons for the impact force. But after the first run of real-life simulation, the chassis is not budging. So to illustrate the plasticity of the chassis, I'm going to use way larger load, about roughly 4,000 times the load of the crush, to simulate the nonlinear physical property of the chassis. And for the convergence analysis, since finite elements have a lot of physical and mathematical constraints, so at the simulation I run into a lot of diverging results. that end with an invalid or error in the simulation. So I did convergence analysis on a very simple assumption and very simple load of 1. And the convergence analysis sees the more load we have and the more convergent it can be. And for crash analysis for real-life simulation of 400,000 newtons, and the principal stress and deformation is fully reflected on the whole chassis with concentration on the bend for the rear for principal stress, and for the deformation it developed from the front to the rear of the chassis, and having the last crossbar to be a lot of deformation. And for the total elongation, the strain we can see the magnitude is to 10 to the minus 7, so it's barely minimal strain. And for plastic strain, that is for our main subject of the study, there's none. So the impact is considered to be way less than what it need to be to show the physical property. But for here, it's very nicely demonstrated that for the frontal impact, for the assumption, the chassis can take the impact. And then for the proof of concept is mainly to show how the non-linear material behavior of the material we define. So I run this with, let's say, 4,000 times the force for impact, and then we can see the stress is to the power 10 to the power of 8. So that's very large, and then it can initiate yielding. And from the deformation, that's a different story. For the same constraint, the deformation is just concentrated on the front instead of the rear. That's pretty interesting, with around 4,000 times of the load horizontally and 2,000 times the load vertically, because for identical simulations it's not going to differ for a lot of results. And then for impact, I think there should be a vector diverging down, so I made it 1-2 relationship, and we can see the magnitude of stress just skyrocketed. Oh no, for the deformation I mean. So the total elongation for the strain is 0.014 to the max. That is way more than the total impact. And then we can see from the contour for the plastic strain, that is the non-linear behavior of the material. There are contours to be seen on the front of the chassis. So I conclude this model to be valid, but the loading for the real-life simulation is too small to show the actual scenario. And we can see from the contours, for the crash analysis, we can see only there's little colored area in the front, so it might be a singularity. So although the result is convergent, singularity might not be eliminated because of the mathematical model and how the nodes are selected. So for the solver, we cannot guarantee there's no singularity. And for more nodes than I have, for our academic use, it's really hard to have it running. Or you need to have a way better license like my friend has in Abacus. So singularity is a deal that we need to figure out how to deal with it. And for the proof of concept, the same thing happened. And all the red areas are in the front of the chassis. So either the model need to be refined, or we need to calculate the node to be in the same spot with concentrations in the model to show how the model should behave instead of having singularities here. But in general, the proof of concept is successful, and we can see a lot of green and cyan colored in the front of the chassis, and then they match with our inertial salts. So the resultant discussion. So the analysis based on crash simulation went very well, but there is a catch. As I mentioned, there's no plastic deformation in real life. And that means for the nonlinear hardening and for the nonlinear behavior of the steel hasn't been shown. But this is a good thing because the frame is structurally robust and then it protects the passenger and the car. Thus, the design compliant with the design requirement from NHTSA. And with around 3,500 times more loading on the chassis, plastic deformation started to appear, proving that the model is feasible and the concept is working. And for the summary and recommendation, the simulation runs successfully with proof of concept, and the geometry is constructed well, and the mesh is generated successfully, although there are singularities that we need to deal with. And the steel cited shows plastic behavior under extreme load. That is the proof of concept. Stress and deformation is selected and calculated, and the plastic deformation is highlighted for the proof of concept. That's easy to see that the model is valid. So the further study of the subject needed to conduct is due to small crash damage and ideal assumptions. If we remove the assumption, it can be better adapted to every scenarios, and then for better estimation of all the chassis, not only for trucks but for cars and all other stuff. So the singularity I have mentioned about, we need to study about that because the auto scale, the red part, is always omitted by the singularity point. And for the reference, that's where I got all the informations. And that's it. Thanks.